Okay, here's an update on the universal resolver. We already worked on that a little bit at the last Rebooting the Web of Trust. We have DIDs now. They're becoming more mature. Resolution is the process of getting from the DID to the DID document, which contains public keys, service endpoints, and maybe other things we want to use. This is a web interface, graphical user interface to the resolver. You can type a DID and it will resolve it. It's pretty much as simple as that. It displays the results in a more or less nicely usable interface. It can show the raw DID document, that it can return some metadata about the resolution process, what happened when the DID was resolved to the DID document. We know we have different methods, right? And each method works a little bit differently depending on whether the target system is Sovereign or Bitcoin or Ethereum or something else. Here's a list of examples. There are drivers for Sovereign, drivers for BTCR. BTCR driver is a little bit outdated. I know that Kim just updated the instructions on how it works. This is an older version. There are examples for VerisOne. VerisOne is really nice because it already returns DID documents, so that the driver doesn't have to do a lot of hard work. So I could try this one, a VerisOne DID, and again it will return, in this case, an RSA public key. And one interesting driver that we added recently was for ERC725. I'm not sure who's familiar with that. It's a pattern in the Ethereum community that is getting more popular for establishing Ethereum smart contracts and for using those smart contracts for key management, updating keys associated with a certain Ethereum address. So I worked with the author of that Ethereum standard to make that DID compatible, so you can have a ERC725 DID registered on Ethereum, and it's still compliant with the DID standard. The tool supports service selection to some extent. So if you remember, those of you who are on the DID calls, we were discussing that to the DID you can add a service name at the end. So you can add, for example, a service name called homepage with a semicolon, and the resolver will retrieve the DID document, and it will select the service that's named homepage. You can see there's a little red line that marks this one as selected. The different drivers, they have configuration options. They can work in different ways. So for example, when resolving a BTCR DAD, the driver could either talk directly to a Bitcoin full node, which is what's happening here, actually running a full node, or it could talk to a blockchain explorer service. So there are different ways how drivers can work internally, and as part of the resolution metadata, they can communicate that back to the resolution client, like what exactly happened, how was the document produced. The second part of my talk, one application of this. So I have the opportunity right now to work on the OrgBook with our friends from British Columbia. We're trying to add DID-based authentication to the OrgBook. And one scenario is service-to-service API. So you have the OrgBook, which exposes an API, and then you have clients which want to connect to that API, and we want to protect the API using a whitelist to only allow API requests from certain DIDs. So we want, and what we're using here in a prototype demo is HTTP signatures, which is a draft specification to add signatures to HTTP requests. And we are adding DID-based signatures to an HTTP request. So an API client will add an HTTP signature, send the HTTP request to an API, which in turn will verify the signature. And so we built a prototype HTTP signature proxy, which is trying to make this very easy. So all the way on the left side, you have an HTTP client, which doesn't really know anything about DIDs or signatures. Then you have a signing proxy. So this is an HTTP proxy, which is pre-configured with a DID and the corresponding private key. This will add the signature to the request and forward it to your target API. And in front of your target API, you have another proxy, which is a verifying HTTP signature proxy. So this one will connect to the universal resolver look up the DID public keys that are part of the signed HTTP request, validate the signature, and then forward it to the target service. So you have on one side of the connection, you have a signing proxy. The other side of the connection, you have a verifying proxy, and you have a HTTP signature in between. This is sort of how you would launch it. You would launch the proxy, pass in the DID, and pass in the private key, and it will sign all the requests that go through it. Thank you.
So one thing that seems kind of cool would be the ability, I don't know if you considered this yet, or if it's even possible, I think there might be cross-origin service workers that you can install cross-origin, which might even work in terms of having like a protocol handler that kicks off to UA, which would, because service workers are essentially HTTP clients basically in software, maybe we could do something where we add like a service worker that is able to connect and sign as your proxy, like it happens locally. I don't know if that's like in the browser we were considered.
Yeah, I think that works too, right? This is one example where we sign HTTP requests done from a client using HTTP signatures, but did auth, the did-based signing and verifying is broader, right? You can sign other things. You can sign email messages. You can do did TLS, which some people here are working on, and you can log into websites and other things.
Just a real quick, easy question. Were you hitting the VerisOne testnet for this? Is this doing live resolution, or?
Yes, it's doing live resolution. There are two DIDs pre-configured here. They are registered on the Veris testnet, one with an RSA key, one with an ED24519
Awesome.
key.
Cool.
Okay, I'm going to talk about a practical implementation of the DID. So just quick background, just to give you an idea of what we're doing. So I work for IXA Protocol. We're basically building a protocol to manage projects and the claims made against those projects for impact work. So if you look at the data model, we have projects, there's a whole lot of claims made against those projects about the work being done, and evaluators evaluate those claims. So what I'm going to demo is the creation of a project, linking a user to that project so that they're authorized to submit claims against that project. How this will work is a user with a self-sovereign identity will create a new project. This creates a project with its own DID and gives the owner capability to the project creator. Another user 2, will make a request to submit claims against that project, which are then going to be subsequently authorized by the project owner. Okay, so the demo, so what we've done here is we've used MetaMask as essentially a credential provider. So we're using the Ethereum wallet address as the DID. It's also the public key. So I'll show you how that works. So if I go here and I say create a project, it'll complain that I haven't yet authorized the credential provider. So I'll pop over to MetaMask, log in quickly. Okay, and then if I go back here and I create a project, everything's template driven in our system. And okay, so let's create a project for, let's say, housing. Okay, I'll do that in Argentina. This is the agent template. So this is a template that's used when I want to register for capability against that project. Let's just turn those off. The number of, let's say, houses that I want built. The template for the claim. So when I submit a claim that a house has been built, what information I need to capture about that. The template that will be used for evaluating that claim. I'll submit that form. What that does is it pops over to my credential provider, which is essentially MetaMask, and requests me to sign the payload of data. So that essentially takes that data and adds a signature that's using a ECDSA encryption, which is then passed through back to the web application and passed to the back end, and it's all verified. Now, if I want to register a user, I've got another app here. I just need to reload this quickly. So that's now created a project with the MetaMask user as the with owner capability against that project to perform certain tasks. So if I pick up this project, so this is now essentially a mobile application. If I want to register against that, register onto that project to submit claims, it asks me for some information. So this is now user 2. And he wants to, let's say, a service agent to submit claims. I submit that. What that does is actually jumps across to another mobile application, which has already been logged in, shows the payload, and the signing happens on that application, and the payload is passed back to the first mobile application, and that data is then passed to the back end and verified. And if I switch back to my project here, you'll see Joe's now been registered, and I can look at the DID information that's been created against that. The status is still pending, but now because I'm logged in as the owner, I can approve the status. And now I need to sign that request to say that I'm actually approving that capability. And when I sign that, then the status will get updated to approved. And now I've established the capability between the project DID and the user on the mobile application to submit claims against that project. Okay. So that's really what I wanted to demo today. Yeah, just some credits. The web application my team built in Cape Town, and then we had a Microsoft team come out from New York, which helped us with the mobile application. And all the code is open source. You can go look at that on our GitHub. And yeah, are there any questions?
I'm wondering about the user interface assumptions behind the interaction we just walked through. The signing dialog box shows a bunch of JSON data that you didn't read, and which I hope no one expects normal users to read. So in what sense can a user interface like this, and feel free to speculate about what should be done instead, in what sense can a user like this be resistant against, you can think of it as a kind of phishing attack, an attack where you try to get the user to use their signature to sign a statement that's very different than what the users thought they were applying their signature to.
Yes, so that's exactly the subject of the paper that I've presented, was how do you make that interaction seamless so the user can, so that data is actually, so you want the data to be rendered by the credential provider because that's the entity that the user actually trusts, okay? So the data, the payload needs to be past the credential provider, but rendered in a way with some other data augmented on that, so that the user knows what they're signing is exactly the data that they're signing, and it hasn't been changed. Okay, so that's one of the issues. So how does that interaction work, and what other metadata needs to be passed across with that information? There's another issue, and that is sometimes that data needs to be augmented with information from the credential provider, and the user needs to know exactly which data was passed from the application and which data has been filled in from their credentials into that payload, so they know exactly what they're signing.
But what is the payload that the trusted, credential provider displays to the user, such that the user can be expected to read the data in order to see that it's what they expect?
Yes, so I think there's two parts. There's the actual data, okay, which is what they're signing, and then there's also information about how it should be rendered. So labels that you can actually associate it, so you can see it in more of a form-based view. And I don't know if that can be standardized so that that all credential providers have a standard interface of how you pass the data over and how you pass the rendering of that data to the user over.
So today I'd like to talk to you a bit about the work we're doing in the province of BC and in collaboration with the Government of Canada and now the province of Ontario. We're trying to solve problems for business people to make it easier for them to do business with the, in general and with the government. And so I'm just showing you here the overall verifiable claims model, which we're familiar with, because what we've come up with is kind of a growth hack to help us bootstrap the ecosystem of issuers and verifiers, of which we have 0 right now. And so what we've created is this idea we call the OrgBook, which is a holder in the middle. And what it's holding is verifiable credentials about businesses, not identities. So there are no DIDs stored in the OrgBook for businesses. I just want to make that clear. What it is it's its own identity that is going to have claims issued to it starting from the business registry and then permits and licenses. So that's our model. And what I'd like to do is give you a bunch of different demos of the components of our network, which we call the Verifiable Organizations Network. The first of which is this public search of public credentials about businesses. So it's a simple search. You use a name. There we go. So you can use a name, and eventually we'll have search by location or search by permit type. So you could say, show me the water taking permits around a city, or show me the liquor licenses around a 1 kilometer block or whatever. And when you click on this, you see the organizational record page, which is a page that's created when the business is incorporated. And it's a permanent page that you could come to. It's going to have a URL that's persistent. It has basic information about the firm and also a bunch of credentials that have been issued to the firm, including, for example, the incorporation certificate, which you can view. You can also click on this Verify Credential button, which is a little bit of a way to try and reinforce that this is a credential that's been issued by the government. What's happening now actually is the OrgBook is asking itself for a proof. And the OrgBook is then providing a proof to itself and verifying this, and we're using the Hyperledger Indy technology for this. So this is just the data that you see. Obviously, we wouldn't show this to an end user. So that's to give the user a little bit of confidence that these are verifiable credentials. So that's fun. We think there's probably some good public value in this from transparency point of view, but this is also all driven by an API which is accessible to any service that is participating in the network. And so one of those services that we've been working with our colleagues in the Government of Canada is registration as a supplier. So this is the supplier registration service, and what we're doing here is we're adding a new supplier record to my vendor record. So I'm a salesperson and I want to register a corporation from BC into the supplier system in the Government of Canada. And I can do that by entering my business information here. I do a search, and what happens now is it's actually asking the OrgBook to verify that data. And when it does, it presents the form. And the important thing here is that this is now providing authentic legal name, which is a real challenge in real systems. Like, the legal name is important for issuing contracts. Sometimes things happen, it's not the wrong legal name, and contracts are issued to non-legal entities. This causes problems. But nevertheless, data integrity is massively increased here. And the user is also given some data that is brought forward by the proof that they can use if it's helpful. If we finish off this registration form and we continue, what happens now is the supplier record is activated, and actually the supplier group is operating their own instance of the OrgBook, and I can look up that registered supplier now, so that applications within the procurement context have an authoritative source of supplier data that is derived from the authoritative source of corporate data, a registry in a province. So that's pretty neat. That's sort of a one-step recipe, let's say, but we've taken it a little further. And businesses usually have a series of permits and licenses that they end up having to get in order to complete their business task. So what we have here is starting a restaurant recipe where we can go through incorporation, and we can go through a series of issuing and verifying. So we click on this. We can we can start a company. We'll just make up a name that's not very meaningful. Type in an address. And what's happening now is this is an independent web service that is simulating the incorporation service. It's actually issuing a verifiable credential to the OrgBook in real time here. We can view that page, and we can see that the incorporation has done. Now what we've done is we've said we want to also register we have to follow this recipe in order to open our restaurant. We won't do the whole recipe.
And we need to wrap up.
Yeah. And now what it's doing is it's actually asking for a verification of that incorporation, which we show down below. So it's actually done a proof request, and a proof has been provided by the OrgBook. And we can fill that form out. And this service now becomes an issuer. So now it's creating the certificate and publishing that to the OrgBook, updating the org record. And then the final piece that is interesting to see is now when I ask for the provincial sales tax number, what's happening is we're doing a compound proof request. We're actually asking for proof of existence of a WorkSafe clearance letter. So it's a zero knowledge proof. And we're asking for incorporation evidence as well. And we can see that down here. So in our data behind the scenes, we can see right here, this is the zero knowledge proof that a WorkSafe letter exists. And then the other claim data, and we can carry on. Now, if that WorkSafe letter had not existed, then this form would not have been presented and the user would not be able to continue. So what's really interesting here is you can kind of have a workflow that's a multi-service workflow. Those services are not talking to each other. They just simply configure their JSON package with the proof requests that they require. And if the service is able to provide it, great, they can continue. If not, they aren't able to. So we're running out of time. But so that's kind of where we're at right now. We have a few other things if you're interested to see. We can show you on the side.
So is this, when you say the verified organization network, are you seeing this as something that is just for BC or something that could grow to be used elsewhere, John?
Well, the imagination is that different jurisdictions would run their own authoritative, like run their own OrgBooks and have services that are able to participate in the network. So they're able to issue credentials to businesses that will eventually have their own wallets. So the OrgBook is a component of the network. The claim issuing and verifying elements would be components of the network in the business context, and that could be a multi-network world. Like that's why we're here partly, is to have sort of interoperability. So there could be jurisdictions that choose, Verus1 or Uport or whatever to route things, but there should be interoperability of claims. So,
and if a business that had a claim issued about it to the OrgBook then wanted to get its own wallet and go get the claim, right, how would you see the OrgBook assisting them in
so
that
we sort of think like we might be able to do something where you can claim your page, and if you can prove to us that you own the business through some business process and some credential that's been issued to you, your organizational wallet, it could then tell you, oh, go off to the various issuers, and you would be reissued a credential to your organizational wallet. These credentials are issued to the OrgBook. So they're unique to that identity. When the business receives its own identity, then it would get the credentials reissued to them.
Right, so
in the future, there would be possibly 2 credentials issued. When you get your permit, you get it into your organizational wallet, and you get it, and one, if it's public, depending on the services requirements, they post it to the,
So from a cryptographic standpoint, the OrgBook is actually a holder of all these credentials.
It's a holder, yeah.
And the subjects being the different businesses out
right.
there. The
it's not holding identities. Like it's not there's no DIDs for the businesses in the OrgBook.
Right.
From a tech point of view.
What I wanted to show you today was how we are building a system to capture ratings and reviews, and how we are late to the party of switching to DIDs, and therefore how we want to switch everything to use DIDs. So what are we trying to do is basically capture ratings and reviews of vendors selling products and services on marketplaces in a decentralized manner. Now, the use case is slightly different from what I see a majority of people here are talking about, in the sense that we want the ratings and reviews to be publicly accessible, but at the same time, shared with a certain marketplace. So if a vendor has a bunch of ratings and reviews, they get stored on a network somewhere, let's say IPFS, and then when they share it with the marketplace, it's an all or nothing share. And that is what is very interesting, because right now what the community here is talking about is you have a complete control over your credentials or claims, and you say, okay, I want to share this bit or that bit. But what we also want to do is say if I share my ratings history with a marketplace X, then they see all my ratings and reviews, so I can't hide, the poor reviews. So that's slightly different. That's the point 2B. And also what is more important is that the verification is slightly different. It's not just signed by a single key, but it has to be signed by a key that is co-signed by the marketplace and the vendor, so that if someone gets their hands on the ratings and reviews data, then they can verify that the rating came in response to a payment which resulted in response from a payment request which originated from marketplace. So it's kind of more slightly involved. So I want to, when we go back, I'll probably be immediately trying to port our system to use DIDs and see how much we can do, and I hope we'll have useful conversation out of that. So what is happening here is you are sending a payment from your address to another vendor's address using the Bitcoin network, and you say you want to send, say, 100 bids, whatever, and say hello. Okay, so what's happening here, what you see scrolling bunch of stuff here, is how we are getting around the problems with IPFS, which is, for example, if I send a review as a customer now, if I was just simply using IPFS, it'll get stored to my local instance, and that's it, voila. But then if I shut down my computer, nobody can access the review. So I need to somehow replicate it. And that is what I've been trying to talk about in the passive storage network. So what we do as a workaround is basically we're running a service node, which we hope other marketplaces will as well, because they'll want access to that verifiable ratings and reviews data. But what we do is, as soon as someone sends a review with a certain op return, right, so it can be identified as a Chlu transaction, we pull the ratings, right, and we kind of pin it on our service instance, right, so on our service node. So that's how we're kind of getting by the problem of replication on IPFS. So what happened here was basically the review went, it got stored on IPFS, and if you look at what the view a vendor would see, yeah, so here it appeared. Nothing magical about all this, but it's coming straight from IPFS, and it's even though we don't have the full verification in place, what I talked about, the verification that was signed by a key, so co-signed by a marketplace and a vendor, that part is still missing in our implementation, but otherwise it's kind of hit there, hit the IPFS, and we're able to pull it back, and we can start running the validations. So just going to switch back to this one. So what we need to do now is move all our work to all the excellent work that's been happening here with DidSpec, right? And what is really bothering me, and I've been trying to ask a couple of people, is how I try to explain that our verifiable credentials are slightly more involved, that you need to do a couple of things to verify something, to verify that credential. So is there any way, and that's what I've been trying to ask everybody, is there any way to specify the steps to take to verify a credential? Right now it's about, oh, it's signed by this key, and that's it. So I wonder if it's possible to do that. So that's something I'd like to discuss. The second thing is the problems with IPFS as a passive store of these verifiable credentials, or any other peer-to-peer network. Right now I see a lot of push in the community about storing them on the wallet itself or on some cloud provider, but I don't know. The next thing is BTC integration. We're kind of still using an API provider, but that's okay. And then on the DID authorization front, how can we make sure that if I share my ratings history with the marketplace, I actually share everything, right? I mean, we have a system to do that, but that a marketplace can check all the transactions going to a vendor or with a Chlu op return identifier, and then see that this guy has not sent me all the ratings and reviews. So that might be one way to do it, but I wonder if there's slightly more elegant ways that can come from the DID authorization itself to provide that. And that's it. So I hope I'll send you more questions as soon as I start work on this.
When the ratings, the ratings that you're creating go out on to some new piece of software that you're writing that automatically pins these specific types of reviews, how is the discovery on that done? Like how does your node that's sitting out there recognize that a new rating has been posted and therefore knows to pin it?
So right now it's complete IPFS hackery. We are using IPFS's pub sub solution. So, you know, we're listening to the same room and then we just replicate it. But ideally, you'd switch that service node to just listen to BTCD, and then any op return transaction type that comes in, just pin it. But that would be problematic because there might be a delay, right? So we'd still have to do something like this. That's why we really need to, I'm really focused on the IPFS problems too as a solution for dApps storage. I think a lot of other people will have this problem too, but yeah.
Yes, I'm just briefly going to mention the some recent work we've been doing on a JavaScript implementation of a DID resolver. So this is very similar to what Marcus demoed earlier. It's a tool for taking a DID and resolving it to its DID document. So we want to have different implementations of this in different languages, and so Marcus Universal Resolver is written in Java, and we're here. I'm going to demo the JavaScript one. So basically, it's quite simple. It has a very basic interface. It's basically just a function that's called resolve, and you plug in a DID, and you get out a DID document, basically. So what you need to do is, when you have a specific DID method, like uport or sovereign or ERC 725 or something similar, then you need to register those methods with the resolver, and then you can resolve them. So it's all very simple. I can just show the some specific implementations of DID methods. We have the uport DID resolver here, and the all that I was going to demo is basically how this looks. You just write a very simple file here. It says you import the resolve function from the DID resolver package, and then you import the register function for the specific DID method. So in this case, it's uport, and then you just run register resolver, and through that you can resolve the uport DID method. So it works the same with other methods. We have a very simple one here for Ethereum addresses. If you're using Ethereum addresses as DIDs, that's a debate itself whether one should be doing that. But again, you have you import the resolve function from the resolver package. You import the register resolver from the ETH DID resolver package. Then you register the resolver, and then you can resolve those DIDs. So it's all very simple, and I was basically just gonna show you you print out the DID documents on a command line. So it's not that exciting. Anyway, I have 1 minute to go.
There's been some discussion how do we make sure different resolvers return consistent results, and how do we agree what methods are there, and how do we maintain drivers, how do we do versioning and all those things. Do you have any thoughts on that?
Yeah, that's a very good question. That has to be some kind of community effort, I'm imagining, because the way this works under the hood is you actually register. This is the this is how it works under the hood here. You basically just plug in the method name, and you say, okay, I'm registering this DID method, and if you plug in something that looks like DID and that name and then something, it will use that method. But yeah, here there is a question of how do we make sure that people don't use different the same name when they mean different things and so on. And that's yeah, that's kind of a governance issue.
All right. This is a recorded demo of the Evernym VCX. You're going to see that on this side, and you're going to see a mobile phone app called Connect.me on the other side there. And what it's showing is the two basic things of issuing a verifiable claim or a credential, excuse me, and then using it. So this right now a connection is being made between a company called Dominion Energy here and the owner of the phone that has an account there. They're doing biometric authentication. They've scanned the QR code to set up the connection and then done the authentication. And ignore the calendar invite there. And the connection has now been made, and we have a connection now recorded in the wallet at the phone. With Sovereign, you're exchanging pairwise DIDs to form a connection. All connections by default use pairwise DIDs. Now, the next thing that's going to happen is the Dominion Energy is going to offer a verifiable credential to Tyler as the owner of this. Now, we're still at an early enough stage. The only drop-down available on this is actually the name of the connection. The rest of the data in a fully integrated product would be obviously sucked in from their back-end system, or this entire process of actually producing the verifiable credential would be automated. He is manually typing it in, as you can see, very slowly. So now, again, the sovereign agent for Dominion Energy as a business here is sending that claim offer to Tyler on his mobile phone. It's going from the cloud agent for Dominion over to the cloud agent for Tyler, and then his phone is notified that the connection offer is there. It still says claim because we haven't updated the terminology yet, but that is happening. So you can see what they're offering, and he says, yes, I want to accept that claim. And it's now, the claim offer is not the claim itself or the credential itself, so now the credential is being issued. Now, while that happens, because it takes a minute under this very early video of this, the claim is being issued, as you saw with John Jordan's demonstration, using zero-knowledge proof cryptography, so that what's accepted in the wallet is going to be a claim that Tyler can now use selective disclosure of the attributes on that credential. So the claim is being, and now he has received a claim from Dominion Energy, and you can see the data that contains. He can look at it directly as the owner of that claim. So now he is, we've finished that first part of Dominion Energy issuing a claim, and now we're going to go to the second part of the verifiable claims triangle, or verifiable credentials triangle, which is he's now going to form a connection with a bank. I believe it's, now in this case, he is generating a QR code. Excuse me. As the employee now of this bank, he is connecting, generating a QR code. And this might be you go into a bank, and he takes his phone. He's getting prepared to, as it generates a QR code here, to now scan that QR code, and he's forming a connection with Chase Bank. Again, in sovereign infrastructure, all connections by default use pairwise synonymous DIDs from both parties, one to the other. The user never, of course, sees those. And now we're going to go the opposite direction. Chase Bank is going to request a credential from Tyler. And they're going to turn around and say, okay, and of course what you request under sovereign is a proof of a claim, and they're going to ask for a proof of home address. And it's going to be from the connection with Tyler Ruff. Those are the fields involved with a proof of home address claim. Again, their cloud agent talks to Tyler's cloud agent, which then contacts his phone and sends the claim request. So there's Chase asking for this information. Now, Tyler's wallet, the ConnectMe wallet, recognizes those claims, autofills them with the claims available from the Dominion Energy, and says, yes, send that proof back over to Chase. And the proof is on its way. And you have the connection, you're seeing that. And I think it ends with it showing up, proof number 1. It's received from Tyler Ruff, and now he can go and look at it. There's the information. About why it says unknown and now it says verified, I think it was actually in the verification process for the proof. And so they have a verified claim, and there you go. That's, there it is.
So on the demo that you showed, you had an example where Chase requested the address from a person. So 2 questions. First, is it possible for the person to update that information in the future?
To essentially subscribe to that.
Oh, okay, so it's a constant stream of whenever the data changes.
Well, no, I'm not saying it is. What you're asking, what I hear you're asking for is could Chase subscribe to that home address so that if it changed, they would get an updated proof? Yeah. And answer is yes. I don't believe that's, Manu can correct me if that's part of the verifiable claims, the scope of the current work, but it would be supported by a protocol of verifiable claims subscription.
Okay, and second question, is it possible to in the future revoke this, this information that I'm sent to Chase and I say I don't want to share it anymore?
Yes. The user can revoke the credential from their side, Tyler in this case. In addition, the issuer of the original claim from Dominion Energy can also revoke that claim, and it would no longer be available to Tyler and his wallet.
All right, so this is mostly a demo about kind of showing everyone in the room that the specs that we're creating here are actually implementable, right? So this is a demo of the VERIS-1 blockchain. It's a fit-for-purpose DID blockchain. It is the world's first public, permissionless, fit-for-purpose DID blockchain, right? It's optimized for identity. Some of the things to note about it, we didn't do an ICO. There's no currency. There's no cryptocurrency. And the reason we did that is to ensure that the network wasn't thrown into debt when it first booted up. And then the other reason was to make sure that the costs were predictable long term. Like over 20, 30 years, you can know exactly how much DIDs and DID operations were going to cost on the ledger. The other thing to note is that it's fast. So Bitcoin, 7 transactions a second, Ethereum, 25-ish. We can do about 209 on the testnet per second now. That's 18 million DID operations per day. And we think we can go much faster than that. So this is the fastest DID blockchain. That's permissionless, right? I think Sovereign could probably achieve about the same amount of performance. Consensus times 15 to 30 seconds with probability 1. What that means is that after 15 and 30 seconds, there's no going back. When you read something off of the ledger after 15 to 30 seconds, you're guaranteed that that's going to be what's there when you come back in 2 hours, 3 hours a week. So fastest consensus time on a public permissionless DID ledger as well. This is our network connectivity. So these are all the data centers that the VERIS-1 testnet is running out of. All the red lines are connectivity, primary connectivity. So that's first tier. Connectivity to those countries. As you can see, we're global currently, and we have a pretty good reach so far. As nodes are added, we expect that to get better. Again, these aren't nodes. These are just data centers. There are many more nodes there. OK, so that's a high-level kind of what VERIS-1 is about. What I'm going to do now is run a couple of operations on the VERIS-1 testnet. So let me make sure that we still have connectivity. All right, so because of the crazy Wi-Fi, thank you to Kim for borrowing her phone. OK, so what are the basic things that you can do with a did ledger? So we're using the did client, right? So there are some basic operations. We can generate a did. We can register it on the ledger. We can add and remove keys. One of the neat things to note about VerisOne is it's all standards all the way down, right? So there's a spec for every single thing in the ledger. We are using Mark Miller and Chris Weber's object capabilities work. VerisOne is a pure capability-based system. There's no access control list or anything there. So we're implementing that spec. We're implementing the latest did spec, and so on and so forth. OK, so the first thing that we can do, the first thing that we can do is generate a did, right? So what this does is it creates a pairwise pseudonymous did. It's local only. It's not registered on the ledger. It's fast. And then the did that we generated is here. The second thing that we do, so this again lives just on my machine. What I can do now is I can register it with the testnet. So if I do did register, and then I want to register this did. I'm going to hit enter, and I'm going to walk you through the process. So I'm going to hit enter. It's going to go out there, find a testnet node, do the write, and within 15 seconds, it will have mirrored it to everything. Consensus will have been reached, and then I can retrieve the did. Right? So that's a 15-second delay from write to getting the did. In some cases, with other ledgers, it can take multiple minutes to hours to get a did back. So I click register. It does an equihash proof. It does an object capability invocation and wraps the whole package up, sends it to the network. It says, please wait 15 to 30 seconds. Let's see if we can get it right now. So I've registered the did now on the ledger. I'm going to do get. And if I get text back, that means that consensus, oh, I'm not getting text back. There it is. Yay! All right. So if you know, I have no idea. I'm going to have to go back and see why I didn't get the first did. But so this is actually coming back from the ledger. So the amount of time that I hit up arrow and get, the ledger had already reached consensus. So you just saw the ledger reach consensus within like 3 or 4 seconds, 5 seconds tops, right? So that's fast. The other thing here, if you'll notice, this is the very latest did spec. So we're using authentication. We're using ED25519 keys. This grant capability and invoke capability bit is the object capability specs that we're working on. So all this, and, this is pretty exciting. Like everything that we've created here is actually implementable and is live on a testnet and it's working. The other things that I can do here is I can. How much time do I have left?
Less than this.
Less.
I didn't start it.
Oh, okay. So I can just go over the other. If people want to see the other cool stuff that he can do, I can show you. We can add and rotate keys. So there's we can actually, the way the VerisOne ledger works is the way you update the did documents is by diffing. So it's very efficient. They're compressed diffs that are cryptographically signed. There are 2 ways of getting stuff on the ledger. One of them is a proof of work. That takes 6 to 9 hours to complete. The other way is you pay money, right? And so this thing needs to be funded. It doesn't use a token, but it does need money to run. And so there are these things called accelerators that anyone can set up. And when you set up an accelerator, you say, I promise to pay 85 cents per did that I create to this VerisOne project. And that gets distributed out to the nodes and everyone else. So you can use an accelerator. This command line thing lets you use an accelerator to fast create dids. So instead of having to do a 6 to 9 hour proof of work, you can get it done in a second, right? The accelerators are pure object capability things. So you basically tell the accelerator, please let me write to the ledger quickly. The accelerator says, that'll be $1, thank you. I hand that over. It does the object capability invocation, gives it back to me. They don't write it to the ledger. They give it back to me, and then I post it to the ledger. So again, a did creation can take under a second with consensus under 5 seconds. Okay, and that's it.
Was what consensus algorithm are you using? Are you assuming asynchronous network, or are you using?
It's Byzantine fault tolerant, leaderless. It's a new thing.
Okay.
But it has mathematical proofs all up and down. So it's a provable BFT algorithm.
And are you assuming partial synchrony? Or?
Sorry, it's the algorithm's name is continuity.
Okay.
So
so you're using continuity. Okay, that's perfect. Thanks.
Okay, so you have a DID, you create a verifiable claim, and you've done other demos to demonstrate that. Where are the verifiable claims stored?
Wallets right now. So this demo, all we're trying to basically show with this demo is the stuff that we're doing here is actually being deployed and it works, right? The previous demo was we need to figure out some way of moving these verifiable credentials through the browser, and at some point we need to hook all these pieces together. So we're not quite there. The assumption here, I think just about all of us know that like wallets are going to be the next big part of this ecosystem, and the wallets are going to hide all of this. You're not going to see any of this, right? You're just going to get a wallet. You're going to say, I want a verifiable credential, much like the Sovereign demo that Drummond did, right? You have a wallet. And then you go to issuers, get your credentials, you have them in your wallet, it's either on your mobile phone or in the cloud, and then you go to a verifier and they ask you for those things. But the assumption here is that the credentials, if they're private, go in a wallet, but as we saw with like John Jordan's demo for the OrgBook, there are plenty of verifiable credentials that should go on the public, in the public space. So for those are going to be public, right? Could be on a website, could be on a blockchain or GitHub. Any of those are valid answers.
Great news here. So the auth that happens here when you create the DID, basically it's a local wallet and you're, okay.
Yeah, So the thing here, if you look in, let me, I think it's like temp did. Did temp, I don't know, I forget what I call it. Test dids, there we go. So in test dids, there are a whole bunch of JSON LD files, and if you look in them.
Private keys are in there.
Yeah, if you want to see all the private keys. You can password protect them. And we're trying to get it so that you don't have to store your keys on your device. You can use UAF type
Thank you.
hardware to do it. Okay, thank you.
Okay, this is a Bitcoin-based DID, decentralized identifier. This particular one is a test one that we created last summer. It's DID, BTCR, X, YV, etc. So what does this mean? So what happens is that we take that last part, and it is a descriptor that is encoding that you basically have a test net. That's the X, the block height, the transaction index, and the output index. So these actually point to the very specific places in the blockchain that you need to get that information. So within that, we basically have some important useful things. Inside the transaction, we have a signature, and we also have an address that is where this transaction previously sent money to. So it sent Bitcoin. This Bitcoin exists in a form such that it has, the transaction, a signature, and it's not been spent. This is the minimum viable BTCR DID. This, in fact, can be any transaction that ever has been used. I could have made a transaction 6 years ago. If it was a standard pay to public key hash and I still have coins on the tip, on the output, I could use that as a DID. So this means that these transactions are censorship resistant. You cannot tell the difference between them and any other transaction that has happened in the past. Now, how can I use this? So I can use it, for instance, to create a verifiable credential. So here is a verifiable credential. You will notice that the creator is the pub key that it got, and it's signed by this value. I have the BTCR thing. A BTCR resolver can go back to the history of the blockchain, of which there are tens of thousands of copies of, and validate that that is a legitimate signature on there. It's valid, and it has not been revoked. So how do I revoke something? So what I do is I basically take the private key that I've never revealed before and spend the coins on the tip, which means it's going to go create another transaction. They're spent, and basically now I have nothing in that tip for that old transaction. I look at my verifiable claim, and it is valid as far as the signature is concerned, but it is revoked because there's no funds on the tip. Now, obviously, we want to be able to do more than that. We want to be able to rotate. So where we sent the funds to, we can put in an op return. That op return basically allows us to give some additional information. Some of that additional information can be things like additional keys. Of course, it now has to be signed by the new key that we just established in the latest transaction. And of course, it points to an address that is the new tip that has the Bitcoin in it that allows you to, in the future, have additional changes, rotations, additional messages that you wish to do. And you might do this many different times. So you spend it, it moves to the next one, you have a new tip. Now you can establish new keys, new DID objects. So that's it for the overview, and we will go now to Kim.
So Christopher showed the process of creating and rotating BTCR DIDs. What I'm showing now is a playground that we created, and keep in mind it's mostly for educational purposes, but the idea that this allows several operations. One is that you can, given a BTCR DID, you can convert it from a TXREF. So actually, to back up a second, what this shows is you could actually enter your BTCR DID either by the actual DID, or like suppose in the case that Christopher mentioned, you have some Bitcoin transaction from a long time ago. You could actually look it up from a TXID and convert it back to the BTCR DID. The difference here is that you do need to specify which chain the transaction occurred on. So the way that we've structured this is to show the phases in BTCR DID resolution. So one of the biggest parts that we spent our early time on was the idea that a lot of the DID comes from the transaction itself, and we typically refer to that as the implicit DID document. But it can't do that much on its own, and we'll talk about what it can do. So we have an extra phase where we can optionally, this one has no additional information there, but we can optionally pull in additional data that was referenced in the transaction and merge it into the final DID document. So what I'm showing you here is actually the one that Christopher just showed you. Mine has a little bit more interesting data, so we can see what that looks like. Here I have, this is common to both of ours. So in phase one, what we've added to this is information about the public key, the hex encoding of it used to sign the Bitcoin transaction. We give it a default capability of authentication. And we have other metadata around the what we call Satoshi audit trail, but it's basically blockchain-specific information that we may use later. It might be things like, if the output is spent, it might show information like that. Down here is the interesting part. So in my transaction, in the op return, I included this link to additional information. In my case, this is what I have stored at that location. So this is just a snippet, just mock example. But note that I've added an RSA verification key. And I've also given that the ability to authenticate. So DID phase 2 is basically just pulling in any additional DID fragments. And then DID phase 3 is everything merged together. So I'm going to wrap it up here, but I want to just quickly point out that, so again, this is used to basically show, it's educational, it shows the steps in BTCR DID resolution, but you can use it as a library. We have the tools that perform the resolving TXRF conversion libraries. They also allow you to create BTCR DIDs, et cetera. So yeah, any questions?
Okay, so awesome. Like, it's really helpful to visualize the multiple steps. Was there anything that you uncovered where the current DID spec didn't necessarily support some of the substeps? Or rather, I guess the better question is, are you going to put descriptions of every single one of these steps in the BTCR DID method spec?
We're putting them in the BTCR method spec. So far, I haven't seen any issues from the DID spec itself. You know, again, as we were working on the BTCR DID method, I think initially we pulled in a lot of BTCR specific implementation details. Over time, we've been sort of converging more towards a DID document-looking thing, and then the BTCR method spec stuff is separate. So no issues yet, but we will have to call out in the method spec, one, the resolution phases, and two, conventions that we made, say, around giving some default authentication capability to the transaction signing key.
There's also a lot of information that we do not necessarily give to the app in the DID document. So the DID document doesn't need to know what the address is that we spent. It's up to the resolver to basically discover that it has been spent and then do the proper thing and get the new keys and revoke the old keys, et cetera, in that process. So I think there's some other things we have to make some decisions on. The other thing is we had hoped that the whole thing could be signed in some kind of thing, and we don't have a structure. So there's no, the app has to utterly rely on the resolver doing all the work. It can't kind of independently take that as a bearer DID document and pass it to somebody else because it could have changed at that point. We'd like to make it more trustless.
Scroll down. I spotted in your full DID document, the one all the way down, the Satoshi audit trail.
Yes.
Can you tell us about that?
Yes. Do you want to talk to that?
So in effect, a blockchain is a signature system. Okay, so the signature system that signs the phase 1 is not your traditional signature system. It is a Satoshi proof. And it's the Satoshi proof, which is all the proof of work, the weight, and everything on the block that verifies that that block is valid. Okay, there's some useful information in there. So for instance, how much overtime have I spent in transaction fees? If I've been updating this over a long period of time, the fact that my transaction fees ended up being half a Bitcoin is actually kind of a relevant clue that this is a DID that I'm serious about.
It's like a reputation for that DID.
Right. I can also post things like bonds, so that tip can have, you know, 10 Bitcoin on it, which basically means I'm tying up the liquidity of 10 Bitcoin on my identity, and so this extra information that you're getting, it is auditable, it's true as far as the blockchain is concerned, is potentially useful information down the line. So we don't know what all will finally go into the audit trail, but we felt that it was useful for an app to be able to know that. So I think that's this distinction that we didn't realize. We were kind of thinking everything had to be described in the DID object, and we're now realizing, no, it's actually our client for this data is the app, and I think that's a new insight.
So will metadata like that be specified in the BTCR method spec, that that's available?
That's right. One thing I realized that's confusing about this display is it shows it as if it's DID document data, and it's not. It is BTCR method spec specific, so we should make that clearer.
To make another distinction, this we have a service endpoint which is called BTCR endpoint.
Right.
And the idea is we actually can store public verifiable claims appended to this document. Okay, so typically these are static documents. They can be in IPFS, they can be on GitHub, anything you can URL to or use a content addressable thing to. And we have some specific tweaks because there's some difficulties. We have you have catch-22s with IPFS and other hash-based schemes, and those will also probably be done by the resolver and will not be not something that the app needs to worry about.
So you could have a dynamic set of claims that were available at that endpoint that, oh, cool.
All right. Thank you, Chris and Kim.